Okay, now previous lecture, what we cover is that we cover a collinear motion in a cylindrical component. So just recap what we covered. So we have covered how to define the position in the polar coordinate, right? We have the R, we have theta, and just be careful in your coming test if this kind of question come up to define your answer in the polar coordinate. Remember the theta is anti-clockwise positive, yeah? For all cases. If you define in polar coordinates, your theta is anti-clockwise positive. You also define the direction of your vector. Right? We use UR and U theta. So we did explain how we relate these two vector on the R and theta axis. Yeah? So if you're not sure, go back to the previous lecture video. Okay. We have come up with the vector equation R and UR, which is the magnitude and direction. And you need to polish up the differentiation under product rules chapter. So for chapter 1, you need to recall or refresh your understanding in the differentiation chapter in your mathematics 1 or 2 about product rules. Then we also covered the velocity equation. Right. It's a velocity equation. V equal to VR UR plus V theta U theta. Okay. So I like always to include this equation in my answer. All right. V equal to R naught U R plus U theta naught or theta dot U theta. So those parameter with the dot above means you integrate time is a time derivative, or you need to take the R and divide it by T, for example, this one. And this one, theta, means you take the theta equation and do differentiation over time. Okay. So this one is more familiar. To find a vector magnitude, you take the square plus square and then you square root. Same with the acceleration. We derive acceleration from the velocity. Okay. So again, this is your homework. Yeah. This is your homework to do differentiation of this equation. Over time, you will get this long equation. Again, in your test, formula won't be given. So we expect you to show your understanding in the fundamental equation. All right. So this we have explained in previous lecture. We have arrived at acceleration equation, this one and this one. All right. So in polar coordinates, you always have the theta axis and R axis, the radial axis and transition coordinate axis theta. Okay. Same, acceleration is a vector, so vector have magnitude and direction. This equation, square plus square and then square root. Okay. And there are 3D cases equation also. Today we look at one example. So example 13, spend some time to read the statement on the screen. I think the diagram already blocked the. Okay. So if you have a hands up in the tutorial in your Teams, oh, by the way, I just upload the new version of tutorial this morning. So you can go to Teams and go to the tutorial folder to download the version 2 tutorial that I just upload this morning, right? So, but the old version you still see in this example 3, I just add on some of the question inside there. All right, so you are given the amusement park ride consists of the chair, all right? Consider a chair, and you know that when you go to amusement park, there is a game where you can go in and the chair is rotate. In this case, the chair is rotating or travel in a circular motion, rotating in a horizontal circular path with a radius r such as arm OB is an angular velocity and angular acceleration theta double dot. Determine the radial and transverse component. Radial is r, transverse component is theta of velocity and acceleration of the passengers. Ignore the size of the passengers in the calculation, because if you include the G inside there, it become rigid body where we cover in the later chapter, right? Okay, so you have the origin O. This is your R axis or your radial axis with a chair. Okay. R is the position 0 to here, and there is an axis of radial. So this chair will rotate, right? Rotate in this direction. We label as B, and O to B is what the question gives us. So the angle is clockwise. Have the angular velocity v dot and angular, right? So again, the swinging direction is clockwise direction. So the question asks us to determine the radial transverse component of velocity and acceleration. In this case, there are no quantity or there's no vector that given you a value here. So if you see this kind of question in the statement question, there's no value inside there, meaning expecting you to derive equation from the diagram. Okay. So the question asks you to determine the radial and transverse component of the velocity and acceleration of the passengers by referring to this scenario. So the first one, when you solve this kind of question, always know your position, or we call it coordinate system. So in this one, coordinate system, you have two axes, r and theta. R and theta. So in this case, because the r is given, theta is given, so this kind of question fall under polar coordinate kind of question, right? So don't confuse with the previous one, the tangent and the normal kind of question, all right? So every time we see a question with a radial r and theta, it fall under polar coordinate question. Okay, so I will just pick the object and then I draw the axis that I have. So this is the path traveled by the chair. And I draw two lines that represent the axis. First is the radial. You can use this diagram to draw, but I pull the diagram and put in the empty space here. So I draw two axes that help me to solve. Again, this is a polar coordinate question. So I will have r and theta. So r and theta axis. And of course, maybe sometimes you need to include the tangent and normal scenario, especially when you have a circular body or curvilinear motion. You need to sometimes consider the tangent and normal. Okay, all right. Now, especially for the circular circle motion, you have this A and T. Yeah. All right. So we have covered the R and theta and the T and normal. Okay. So this is the tangent direction. This is the normal direction. This is the R direction. This is the transverse direction. Okay. Now, before you solve, you have to know where is your positive, where is your negative axis. Yeah? So if you're increasing in your R in this direction, means you get a positive value for your R. If you're increasing in transverse coordinate theta in this direction, meaning you get a positive value for your theta. Same with this one. Your motion, your object travel in this direction. So the positive tangent direction is over here. And you know that the tangent and normal always 90 degrees. And you know that to keep the object in the circle, your normal direction always pointing to the origin of the circle. Okay, so this is what we learned in the previous section when we talk about tangent and normal. Okay, so there's an O here, origin here for the circle. Next, we move on. We take away our diagram and we focus on the schematic diagram. So expect something like this in your coming test one. So you need to draw a schematic diagram to represent your answer. So then we define our acceleration and velocity. So what we have is that in the previous derivation of our velocity and equation, we know that our velocity and acceleration related to r and theta. So this one is theta, typo error. Right? Okay. So we know that our r or our radius vector always constant because it's travel in a fixed circle. So our r vector equal to r before we start. Then when you differentiate your r over time, there's no change of your r because your object travel in a fixed circle. There's no change on this r. Okay, so r equal r, and then you differentiate one time to get the changes of your r. R dot equal to 0, and if you want to differentiate one more time, you still get 0. So r double dot equal 0. Now, what is the reason why we do all these three derivation? Because previously I showed you this morning before we start this example, your acceleration equation, you have r ur plus a theta u theta, and your ar equal to r double dot minus r theta dot square times the ur direction, and for the acceleration at the transverse direction, r theta double dot plus 2r dot q dot. Okay, that's why you need to find what is your theta differentiation, right? Same with the velocity also. Okay, your velocity equation, v equal to vr ur plus v theta u theta. So to find your vr, you need r dot in the blue color, ur plus, if you want to find the v in the transverse direction, you need the r times the theta dot times the u theta direction. This is what we learned previously. That's why when it comes to this question, you need to derive from the equation, from the diagram, sorry. That's why first steps is solving this kind of question. Ask yourself, where is the location, or plot your coordinate system. Or in other meaning, we expect you to give us the axis using schematic diagram. Draw the object, draw the path, give us the axis of r, theta, and if you want, you can include tangent and normal in your diagram. Okay, so this one, you will see this one later. Okay, but normal for polar, r and transverse direction axis is important. All right. So just now we stopped at r. R is the radial vector. So you at a starting point and all the time your r is fixed. So no matter how you change it, you divide by time or you have a derivative over time using your r vector, you still get 0. And you double differentiate or you have a second order time differentiation, you still get 0 because this one refer to this one. You differentiate 0, you get 0. How you get 0? Because you differentiate r. R is a constant. You differentiate constant, you get 0, right? So let's say your x equal to 3. You dy dx. What do you get? You get 0, right? So same time with this one, but this time you differentiate over time. There's no changes of r in this case, right? Then you talk about your velocity vector. So your chair is moved in a circle, but at that particular point, you have radial direction and transverse direction. And at that particular point, you know that from the previous session where we talk about velocity definition for velocity vector is always tangent to your curve, right? So tangent and theta always on the same line. So your vector is along the tangent axis and the transverse axis in this case, right? Then recall the definition of acceleration also. So in the previous lecture, we defined the acceleration in the transverse direction. In this case, the acceleration in the transverse direction is on the line of transverse axis, this one. Okay, so I label V and A theta. Because this question asks us to solve velocity and acceleration of these passengers or of this chair. So on your schematic diagram, this is the basic information that you should have on your answer, right? So first, you have to define your coordinate system. We give you the r and theta, radial and transverse axis. Then give us your path of your object. And you can draw an object, or you can just give us a big ball or big circle here, just to represent your object. Then put in what question asks you, right? The velocity, the acceleration, and so on. Okay, any questions so far for the schematic diagram? Attendance.
So far, no, sir.
Shilton, are you there?
Yes, sir.
All right. So, in this case, your R is in this direction. Later we will calculate your acceleration in R. We know that based on our schematic diagram, our acceleration in the radial direction to maintain the position in the circle, our acceleration will be going this way and not this way. Huh? If your acceleration going this way, your chair going to travel in the bigger circle and bigger circle and bigger circle. Okay, so in this case, you're always having a constant circle. So your position of your chair is having an acceleration in this direction, and this direction is opposite of your R direction. That's why there's a negative there. Okay? So you have your acceleration theta, acceleration radial. However, in this case, the magnitude is negative because it's go against your R axis positive direction. Okay, before this, we already defined all our positive direction is in this direction. However, acceleration to maintain the position, it have to go opposite of your R direction. Okay, recall the velocity equation that we saw that show you just now. So V equal to R dot UR, and again, remind yourself, velocity and acceleration, they are vector. So vector always have magnitude and direction. R dot is a magnitude, UR is a direction. R times theta dot is a magnitude, U theta is a direction. So basically, you have direction in the first section there. You have direction in this direction. You have vector in this direction, right? This gives you two directions. That's why from this vector equation, you can find the magnitude and the direction, right? With the square plus square and square root of the magnitude, and the direction gives a trigonometry tangent, inverse tangent of the y and x, or the r and theta. So I just rearrange the equation. I just take out the bracket. Okay, so this come by pair. You can straight away use this one, or you can use this one if you can translate lah. But normally when I define velocity in the polar coordinate, I will write these two equations so that I won't confuse myself. So from the equation that we derived just now, on the R component, substitute your R value inside the equation, but in this case, you know that the R dot is still missing, right? This is the acceleration equation that I showed you just now. A equal to vector plus vector, vector in R direction, vector in transverse direction. So R double dot minus R something, R theta double dot plus something. So you have these two equations. So basically, when you solve polar coordinate question, this 4 equation is very famous, and this is also what we're looking for in your answer. So in your answer, if you write this one, this one, this one, this one, minimum marks, you will get 2 marks, or sometimes when we become generous, you have 1 mark for this one, 1 mark for this one, 1 mark for this one, 1 mark for this one. But minimum, you will get 1 mark for this set, 1 mark for this set. Okay. All right. Again, equation won't be given, so make sure you memorize the form of equation. So we back to the velocity equation. We know that R dot is 0, so you can cancel the front one. So the velocity vector become R theta dot. Same with this side. You can cancel the R double dot with 0. This one also cancel. Right. Okay, this one cancel. To rearrange, you will get okay, you will get minus R minus r theta dot square. I don't know. Okay. So this one you have two components. Yeah, just now I was looking for this one. Right. So remind yourself that this is the r component. This is the theta component. So you have minus r theta dot for the r component. So you have ar equal to minus r theta dot square, which is represented by this one. And this one will equal to this one, because this one you cancel already. So a theta equal to r theta double dot. So we have v ar a theta. Okay. Any question for this very simple derivation? Any question? And this kind of question usually will be in the first section, which is maybe, for example, question 2a. Normally, it will give you to derive the equation for this one. And then section B, I will give you the assumed number. For example, I give you if the R is 100 meter, for example, or maybe 30 meter, and I give you the angular velocity of this one. So what is the magnitude of your R, for example, okay? So this one is just introduction of application or derivation of equation. So we can give you, we can extend this kind of question into a scenario where we give you if R equal to a certain value or R equal to an equation, right? So you have to do derivation. Oh, sorry, not differentiation. Yeah. Any question before we move to next example?
No, sir, so far.
Okay. Right. So next we look at another example. Example 14. Spend some time to read the statement on the slides here. So you're having a rod, right? A rod, and this L rod is rotating in the anti-clockwise direction, theta. You see the arrow, all right? So you can see a clear picture in the tutorial handouts. So you have the L bar that this OA is rotating in the anti-clockwise direction, and there is a ring on the bar here, which is labeled as B, and as the rod is rotating, the B, because of inertia, B move from the O to this location, or it can even slide further. Okay, so we are given at that particular time, the location of B is given by R vector. Okay, so you read the question again, there are some equation given. Rod OA rotate in the horizontal plane means there is no change of your z-axis elevation. You study as a two-dimensional question. So rotate in the horizontal plane such that theta equal to t cubed a radian. Okay, in this case, a radian is used. At the same time, the collar B or the ring B sliding outwards means because of the inertia, the ring will slide outside along OA so that the R equal to another equation. R equal to 100 T square mm. In this case, the unit is mm. If in both cases T is second, determine the velocity and acceleration of the ring or collar B when the time is 1 second. Okay. So this kind of question is important when you're designing a mechanism that is moving dynamically, maybe in a vacuum chamber, or you have the devices that that control, right? So this kind of behavior that you can find in a gyroscopic, all right, gyroscopic devices and all these. Okay, let's continue. So first, always look for your coordinate system or your position. So from here, on this diagram is very empty. So what we expect you from the diagram usually is your schematic diagram. So schematic diagram always come with the axis, right? So okay. So in this case, just a reminder on this scenario, the time parameter equation of the path is given because the equation is given. So in this case, you don't need to consider the more complex issue where you can stick to this equation in your solution. Yeah, anyone you have question? I hear your something dropping. Right? So if you do not have question, remember to mute your mic, right? Because your input will come to my side in the recording. All right. So I will just draw the scenario. So I draw the rod. And I input the axis. I have the rod OA and the collar B as a schematic diagram. So I put in my axis as usual. Right? I put in my axis as my usual. And an object axis also. I have two objects here. One is the OA. One is the ring. So I just put in the axis for reference. And I put in the path, right? Because this rod doesn't extend or doesn't do anything. The length of OA always there. However, something dynamic movement happen here is your collar is moving as you swing your OA. So there's a path about this profile will happen to this collar, right? I mean, you try to imagine if you B is at the O and you try to swing this OA, what happened to B? If you look from the top, the B will have a parabolic movement, something like that. If you view from the top, right? So you view from the R, it will move from the origin until to the certain system, and you're given this equation. This path was given by this one, right? Collar B sliding outwards along OA so that R is 100 T square mm, meaning the distance B travel from origin was given by this equation. This is the path, or this is the path of this blue line. Okay. And I start inputting the axis R. Okay, just a quick one. Just a quick one. I think you have no problem identify the R positive direction. I have question to ask. Why your theta is in this direction and not that direction? Why? Steven, are you there? Steven?
Yes, sir.
Why your theta axis you can label in this direction? Why your transverse axis is positive in this direction and not this direction? What do you think? Why do we put our positive axis in this direction?
Because it's moving in that direction.
Correct. All right. So it's easy to identify the axis positive direction because the question already tell you you see the arrow of your angle. The angle is anti-clockwise in that direction, and your OA rod is moving in this direction. So this is your theta direction. Don't label the wrong one. So this one always follow the theta direction. Okay. Of course, if you want to label your theta here, no issue, but you will see a loss of negative value in your derivation later on. Okay. I myself, I don't like negative value, but if you still want to use your theta over here, go ahead. There's no wrong answer if you put your theta over here. Meaning all your answer, your positive direction to this direction is positive. So every time when you input your value later, because your rod is moving that direction, so you need to remember to put in the negative sign in your answer if you label theta over here. Okay, so I myself, I like to put follow my movement of my object so that my answer will always get positive value. Okay, we settle r and theta axis. So I'm going to put in the velocity and acceleration direction. So we know that our B we're going to slide outwards in this direction. So this is my VR. Okay, this is my VR. You know that when you solve polar coordinate question, you need to solve, if you go back to the equation of your V, you have your VR and V theta. So basically you have two vector for the velocity. So you have VR and V theta. Again, the V theta in this diagram is at that particular point that is tangent to the path. Okay, as this one move along, the direction of this one will be different because the velocity always tangent to that particular point. Okay, you have your VR and V theta. So I know that I can draw the resultant of my velocity with the vector diagram. So I always draw a square to combine these two because these two are at the 90-degree perpendicular to each other. So I can use a square or rectangular approach to solve the resultant. So of course you can move this one to here to solve. So you can always transfer the magnitude and direction of a vector to a location to solve the vector diagram. Okay, as long as you don't change the length of the arrow and direction of the arrow, you can build the vector diagram. So this is under vector syllabus or in your maths. So you know to find this one, you take this one plus this one, right? So V, and the direction of rotation of the rod is anti-clockwise direction, theta. So the angle of changes over here is not same as this one. Okay, you have two angles there. One is the rod angle. The rod angle follow the question, theta. Here to here is theta. However, the resultant vector angle from the r axis will be given by a new one. We call it delta. Delta measure from here to here. Okay, don't directly import the angle into here. It's not same. Because this one is referring to the rod. This delta referring to the vector, velocity vector. It's a different angle. Any questions so far for the theta and angle and delta? Good. Okay. Next, I focus on solving the question already. So this kind of question is what we expect from you. You always give us a schematic diagram with the axis. All right. And normally you start your diagram with a vector velocity diagram. So this is our objective, right? The question asks us to find the velocity at 1 second, right? So I just copy the equation from the question. You have R equation. You have tangent equation. You have a transverse equation also. So to solve, what is the position of your R when the time is 1 second? So you use the equation 100t squared. You insert or you substitute t into the equation, you'll get 100 mm. So the color here will travel the distance from origin to t equal to 1 is 100 mm. So what happens if you, what happens if you differentiate over time? Don't take this number to differentiate. You have to always go back to the equation to differentiate to find the R dot or R double dot. Okay. Again, why we need to find the R dot and R double dot or even theta dot or theta double dot, because in our velocity equation, we need to use the R dot and the theta dot. So you need to do differentiate over time. Okay. So if you differentiate your R equal to 100t squared, you differentiate over time, dr dt 100t squared, you differentiate over time, it's like you do dy dx. So this time you focus on t. So 100 remain. When you differentiate over time, 2 move to the front, 2 minus 1, you will get 2 multiplied by 100. You get 200t. This one exponential minus 1, you get 1. That's why when you differentiate r over t, you get 200t. Differentiation scale. Differentiation scale. R dot means the r dt. Okay, the r dt means r dot. And you substitute t equal to 1 second, you get 200 mm over second. Your unit change already. R become r dot, r become r dot. R dot is changed over time. In this case, mm over second. Normally, careless mistakes is here to here. Some student, you're going to give 0 in this line here because they forget that R actually is an equation and not 100 mm. Okay, so this example, you start to see application of differentiation that you learned in your mathematics. Okay, so what happens if you double differentiate or you differentiate one more time of your R dot? So you need to take the 200t and then you dt again, you get 200. Okay, so if you calculate R double dot, you transform 200t become 200, and then you substitute t there, you still get 200. Okay, so R double dot means you differentiate the equation of this one over t, get 200, you still get 200. So the answer, but the unit change from 200 mm over second square. Any question from R to R dot, R double dot? Any question? Any question?
No, sir.
You should able to see the reason why we find R dot and R double dot. There's a reason there. because your vector equation, your velocity vector equation and acceleration vector equation, you need to use the r dot, r double dot, and theta dot and theta double dot. I've shown you how to do the r. You apply the same for transverse direction. So I put the answer over here for your r derivative. You do the t. Okay, so just test your differentiation. What happens if you differentiate this equation over t? D theta over dt, what do you get? Let me ask some of you. Prem, are you there? Prem?
Yes, sir.
Okay, Prem, when you d theta over dt, what do you get? First differentiation, first order differentiation, what do you get?
3t square.
Again?
3t square.
3t squared, correct. Okay, very good. So this is the original angle when you have time equal to 1 second. So again, this is radian. So you get 1 radian. 1 radian equal to 57.3. Okay, how you get this value? 360 equal to 2 pi radian. So 1 radian equal to this one. So you do first derivative, theta dot, you get 3t squared, substitute 1 second there, you get 3 radian over second. You do one more time, second order derivative, you differentiate one more time, you get 60, substitute 1 inside there, you get 6 radian over second square. So far, you get r dot, r double dot, you get theta, theta dot, theta double dot. You have all safe value. Recall the velocity equation and acceleration equation. Substitute inside there, you get the answer for this question. Okay. So these are the 6 expected answer. So just recall. Okay. So you just substitute all this value inside the equation. Okay. VR. Okay. V sub r equal to r dot. Where is r dot? 200. Copy the direction UR. R theta dot. So your R is 100 when at 1 second. What is your theta dot? You already calculated 3 radian per second at that particular time. So 3 here, 100 times 3. This is the vector direction. So the answer for velocity is 200 UR plus 300 U theta mm per second. Again, for this module, if you're given a quantity, always remember to give back the unit. Yeah? You don't need to put unit in your calculation steps, but when it comes to your final answer, remember to put back the unit. Yeah? So this is the vector equation. You have your r magnitude. You have your theta magnitude. In this case, if you see this one, okay, let me ask a question. Nageswaran, assume you already get the answer for this equation. Compare side by side this one and this diagram. My question is, what is the value of this component? Nageswaran, if you compare this equation and this diagram, what is the magnitude of VR?
Should be a 200 UR.
200 UR. But this is a magnitude. This is a vector, correct? This is when you write VR here, it means the magnitude. So this one is 200. Yeah. UR is direction. Okay, so very good. So this one you should understand that V theta equal to 200. Basically, you have two magnitude over here. You should be able to find the resultant V direction. So you use the traditional equation, square plus square, square root. Okay, this one square, and then you square root, you get the answer for magnitude of your V, which is 316 mm per second, but the value is not important. The value is that you understand why and how you get the resultant magnitude. Okay, you have the UR and U theta, you're able to find the angle of this one, right? So you're using tangent equation. Tangent of this delta equal to V theta divided by VR. You do the inverse, you get this angle equal to 56.3 degree. However, don't stop here. The question asks you the velocity direction from the origin theta. So the total angle, always remember to add this one and this one. The final answer for the direction of your velocity is 114. How you get 114? How you know that this angle? You already find, right? You already find your 1 radian here just now. 57.3 degree over here. You already find the angle over here. So this one plus this one, you get this answer. Okay. Next, you do the same for acceleration. If you understand the velocity, you should be able to do acceleration. However, just to be careful on the direction of your acceleration vector. You have your A theta, and in this case, to maintain the curvature motion, your radial direction is into the origin and not this direction. Okay. So from here, you can find the vector also, the resultant vector. Okay. Using this concept that you apply for the velocity just now. So A theta, AR, this is the resultant of your R. So we start plugging in and this is the angle phi from the R axis or from the AR vector. We have one angle over here. So again, recall the equation for acceleration. We have these two, and I've shown you since the beginning. You already done the derivation of the R and theta. So just substitute inside there. Okay, substitute all the value of your R double dot, theta dot, and so on. You rearrange, you get this equation. A equal to minus 700 UR plus 1800 U theta. Remember to give the unit mm over second square. Okay, acceleration unit. So from here, you should be able to identify which one is AR, which one is A theta, right? By comparing side by side the equation, you should be able to input your value over here and find what is your A. Okay, so A square plus square square root. You get your the acceleration magnitude is 1930 mm over second. Again, the number will change, so try to understand the strategy we saw for the A. Angle also same. You move this one to here, you having a triangular vector. Angle of this phi here is 68.7, but what is important, you know how to find the angle from the vector diagram. Total angle, always remember to add the origin angle. In this one, this is a special scenario. You always need to check where is your origin axis to the object. In this case, we are focusing on the ring. So the total angle is 169. So how to get 169? Again, go back to your calculation just now. You already find what is this one. How you get this one? How you get 57.3? Question already give you one equation. Theta equal to t power 3 in radian. In this case, question asks you 1 second. So substitute 1 second here. 1 radian equal to 57.3. Okay. Okay. Any question before we go for a short break? Let me stop the recording.